Hey, hi everyone. I'm Amit Golander, Plexistor CTO. Before we begin, I'd like to wake you up. I was promised this is an interactive forum. I could have done this lecture without anyone asking anything at home, and I flew quite, several long hours to get here. So please do participate.
Do you really know what you're asking for?
Okay, almost everyone participated. Okay, so in this session I'm going to go over the technology primer, basically explain some of the design assumptions, explain some of the features, not everything, but we'll leave something for next time as well. Okay, so a lesson learned from storage field day. I'm going to start with making sure that everyone understands what we have here. Okay, and what we have basically is an enterprise-grade storage system that doesn't look like an enterprise-grade storage system. Okay, so it's very different than what you, at least the storage guys here, are used to seeing. It's not a shared array, NFS or SAN. It's not a virtual shared array like SDS solutions. They're basically implementing the same concept at the server layer, but still maintain this distributed, uniformly distributed view of things and through traditional APIs. What we decided to do is to take a different approach. We have the local file system facade that almost all applications work with. And we've decided to hide the entire enterprise-grade storage with all the features and all the distributed cluster and everything else underneath that. Okay, and I'll show a bit later why that's useful. For the user, they don't really need to config anything. Well, not anything. There's some parameters, but they basically use a local file system that's called M1FS. And they get all the features within that.
Is that your own file system?
Yeah, built from scratch, specifically to be byte addressable. So it doesn't have I'll show that in a second. Okay, so the first thing we want to do is we have this storage class memory technology. We want to know how to basically buy that and where to place that within the system, right? And SCM is not really a single technology. It's basically a tribe. So there are several families of different technologies. We have MRAM or an STMRAM and several different types of MRAM, different flavors that are very high speed, actually faster than DRAM sometimes, but less dense, so pretty costly. Then we have 3D crosspoint, and then we have ReRAM. And resistive RAM is, for example, a lot slower than memory, faster than flash, but a lot slower than memory, but then supposed to be cheaper than flash in the long term, right? So we have this different choices, and what we choose basically depends on the application requirements and where I place that within the system. Okay, I'll make different choices along the way. The important thing is that it's byte addressable, as Sharon mentioned, and it's near memory speed. Okay, it doesn't have to be memory speed, but near memory speed at least. And we want to make sure we place it in the right location. So there are two popular ways of packaging storage class memory. The first would be an NVMe drive, okay, which is a good fit, for example, for ReRAM. And then the second one would be persistent memory or non-volatile DIMMs of different types, which are based here on the memory interconnect. Okay, and that would be, for example, a perfect choice for MRAM. Now with 3D crosspoint, which is kind of like in between, you can have two different flavors. You can use it as an NVMe device, and you can use it as an NVDIMM device. And Intel basically already announced that they're going to do both. So you're going to have Optane as an NVMe device, and you're going to have to Optane as an NVDIMM device. And I think they also mentioned that the performance difference is between a 7-time acceleration for the NVMe device to 200 times for the NVDIMM device. Right? So there are several fundamental aspects of computer architecture that you have to take into account If the data source, the consumer and the producer of the data is the CPU itself, then you want to put it as closely as possible to the CPU itself, just because you enjoy the entire memory subsystem of all the hardware caches, atomic operations, everything else that's basically built into the CPU for memory, and now it can be leveraged for persistent memory as well. And the access times are actually lower than 0.1 microsecond. Then, if you're not doing that, you have the I/O subsystem, which is basically not optimized for latency; it's optimized for throughput. And obviously, you don't want to place it like hard drives or the flash devices, SATA flash devices on a SAS or SATA HBA. You want to place it at least as an NVMe device, so directly on the PCIe interface. And then you're obviously going to have slower access unless you're accessing, the consumer and the producer of the data is actually across the network, like the brick that Sharon mentioned. And then I can actually place it here as an NVMe device, and I probably don't have to invest as much money in MRAM-like technologies. I can basically go to cheaper technologies because I'm already having a higher latency because of the fabric itself. So basically what I wanted to explain is that you need to purchase the right SCM in the right form factor and place it in the right place according to where your data is being produced and consumed. Still no comments I see from the audience. So
one thing I was just going to ask about the latency from the NIC. And if you were then reading, you're talking about low latency across the NVMe device on the PCI controller.
Right.
If your NIC connected to the PCI controller and still reading over the network, that latency is going to be much slower than even via a SHBA.
Right. So I'm going to show some numbers later, but you're absolutely right. I mean, there are different trade-offs. Otherwise, we wouldn't be here. You need to choose between cost, performance, and operational considerations of ease of deployment, for example, of SCM within a data center. You need to choose what's right for you. And I have a Flexi-Plexi slide that basically shows that we're very flexible and you can configure, basically build different systems according to those trade-offs.
Okay, so you can have on the CPU next to the PCI controller or across the network.
Right.
But obviously across the network you're going to be losing some of that super speed. But then you've got the advantage which you were talking about earlier of carving up the single block and pointing it to different servers and.
Right. Exactly.
Okay.
Cool. Okay, software considerations. So for I think 5 decades now, for long decades, we've had these assumptions for storage, which are not really relevant for SCM, and I'll go and explain that.
It's only about 3 decades.
Only 3 decades.
Yeah, block abstraction is relatively new.
Okay, so we have software layers.
Hey, he said I should talk up.
That's true. I opened that door. So software layers is something we're very used to. Software layer, everything in computer science could be solved by another software abstraction layer, and that's almost true. The main thing that can't is latency, and latency is our primary design goal. So having many layers like we've been used to in the storage stack is not a good thing. It's very flexible, but it's terrible for latency, especially if the device itself doesn't really have its own latency. It's close to zero latency, and then everything becomes software latency. So the first thing we wanted to do is basically remove all these 6, 8, 10, 4, regardless of the exact number, depending on the functionality that you're putting in. We want to remove that and basically replace that with a single layer, at least for most of the cases. Okay, it's not entirely true for all the cases, but at least for most of the I/O accesses, that is true. And I'll give some examples later on for that. The second thing is network. So obviously storage, started as direct attached storage at the beginning. but with EMC and NetApp and all the others that came along, storage was a lot of time consumed over the network. And what that basically does, it adds the network latency, which is significant, as I said, with hardware that has almost zero latency by itself, the storage media itself. And then it also adds up multiple software layers, both on the client side and the server side, on top of what you have for the storage itself, right? So that adds a lot of latency as well, and you want to get rid of that. As I said earlier, you want to place the media itself as close as possible to the producer or consumer of data. So we've given up on that approach as well. That doesn't say we are not using the network. We are using the network, just in a very different way. Software caching. So when hard drives and flash were here for the single truth of the data, having memory in front of it was very logical as a caching device. When you switch the storage media, the persistent storage media itself, to something that is memory speed or near memory speed, that makes no sense at all. I mean, there's no good reason for investing additional resources for software caching when the device itself is almost at the same latency. What that does is adds cost, obviously, and then it also takes away your memory interconnect resources and your memory subsystem resources, just because you're moving data around through the memory controller or through the interconnect, and you're wasting resources. But that's so software caching has to go away. At least the naive software caching, the Linux front, the page cache, all those mechanisms. And finally, the block abstraction, which is very, very fundamental to all storage solutions today, except the ones I'll show in the next slide. But basically, all the commercial storage solutions out there today are focused on or are based on the fundamental assumption that there's a block layer underneath them. And taking a byte addressable storage media like storage class memory and wrapping it up with a block addressable wrapper, software or hardware wrapper, obviously can be done. Obviously, a lot of people will use that because they will use 3D Crosspoint, for example, and that's the exact approach they will use it with. The only problem with that is that it takes away most of the advantage of the device itself. And I'll give some numbers in.
You're still abstracting it with, instead of using block abstraction, using file abstraction.
Right.
How's that then different from a abstraction layer?
So a block abstraction layer basically means that if you're changing, let's say you have a snapshot counter, reference counter, right? And the only thing you want to do is basically increment that counter, right? So instead of going to if it was in memory, for example, you would go and increment that, right? Maybe even atomically, in an atomic operation. Instead of going and changing those bytes that you actually want to go and change, you're basically wrapping that up and reading, 4 kilobytes, for example, in the best case scenario of a block, changing that within that, and then writing 4 kilobyte back, right? So it's very inefficient in that sense. Now, if you're doing really large I/O, maybe it doesn't really matter that much, right? But if you're only changing small portions of the data, which a lot of time is the case. I mean, most of the metadata that the file system layer adds and that the application layer adds, or the middleware on top of that as well, it's really small chunks of data that change. So that's kind of the reason. And I'll actually show an example with 4 kilobyte writes. So with blocks that are 4 kilobyte aligned as well. So kind of like the perfect example, but you still see this huge gap in performance. I'll show that in a bit.
So the file abstraction then, okay, if we're talking about byte...
File is just for management purposes.
Okay.
Right? So it's not for the data access. So the block abstraction is actually for data access, not just for management purposes.
Okay.
So it's in the data path. It's not, out of band like the file abstraction layer. Okay. So another interesting property, and Sharon mentioned that, is the duality. right? So that's obviously not what we do. That's physics. But particles have the they have you can view them as wave, or you can view them as particle, and that's basically the duality. But storage class memory is also the same way, right? You can access that as if it was memory, and you can access that as if it was storage. And basically, it's up to the application to decide what they want to do, right? So we have the applications here on top. Then we have an I/O path, a traditional storage I/O path, which is the read and write system calls. And then we have the memory path, which is basically, again, the mmap system call and the msync system call. And then I would just issue load and store assembly level instructions to access the data, right? So those are around for a very long time. I mean, it's nothing new. Just the implementation underneath is new. I mean, this used to be cached in memory before it reached storage, and this actually is cached in memory as well before it reached storage. And what we have now is for the first time, we have a device that's capable of this duality. I mean, you can access it directly either as storage or as memory. And we need some software in the middle that can do the same. It can basically allow that capability to flow up to the application layer, surface up. So this is a slightly deeper view, right? So we have Linux underneath. We have the PMEM driver within Linux that basically manages the allocations of the memory addresses of the devices. It's not in the data path. Okay, it's just to basically put aside the NVDIM addresses, put them aside that the operating system doesn't use them as regular memory. And on top of that, we have basically hopefully a PM, a persistent memory aware file system. Hopefully, it also supports direct access to the device itself. And then we have Linux VFS and virtual memory layers as well to basically capture those system calls and traditional as the data, but not in this case. Okay. So before moving on, is this kind of clear? Okay. Now there's a new programming model from SNIA. And there's a new library, NVML, and the NVM library that has been released a couple of months ago. Its first version. There's a lot of confusion there.
It's from SNIA. I'm suspicious.
Okay. So there are a lot of good things within NVML. Most of the confusion in the industry at the moment is that people don't really understand how it works. So I'm just going to explain that for a second. What that basically provides, it's a library, it's a user space library for the applications, for new applications or for modified applications that they can use. What that does is basically it uses the traditional memory path behind the scenes, right? And then it goes through the same flow. It requires a direct access feature. So it requires the DAX support from the file system. There are currently 4 file systems that support that. For Microsoft, that would be ReFS. For Plexistor, obviously, supports DAX as well. And then you have within Linux XT4 and XFS that support DAX as well. And I explain some of the trade-offs in the in this slide.
But it's only for new applications. You have to rewrite your application for it.
Right. So for NVML specifically, you need to rewrite the application. I mean, it's not just rewrite the application, it's a new programming model. So you need to learn this new programming model and then use it. NVML basically allows you an easier path to doing that. But you can also benefit from DAX without the NVML, just using the traditional code without changing the application. Basically, what that does, it saves you one of the copies. So instead of copying the storage to the page cache and then using it from there, load and store instructions to that surface, and then copying it back to the storage, you just skip that and you access directly the device. So you don't have to have the new programming model in order to benefit from DAX, but it does work the other way around. You do need the DACs to benefit from NVML. Okay? And basically what we want to do is we want to be able to leverage the SCM regardless of the path that we chose, right? Okay, so what I'm going to do now is I'm going to survey what are the other options that exist for those paths, and then kind of see what the difference is, in a very high level. Okay, so we have PMFS and Nova. Both of them are, PMFS is deprecated already. Nova is a newer, I would call it academic prototype. So it's not a commercial offer. But basically what they do is they provide you with really fast storage. So they leverage persistent memory devices to accelerate this path, right? They don't really they're not DACS compliant. They don't really support that path. So you can use them to accelerate the I/O path itself. Right? If you try to use them in the other manner, you're basically still going to copy things to the page cache and use it in the traditional manner. So I've listed down several of the cons that those offer. For instance, they're unoptimized. So there are several things that are more complicated to support. For example, efficient support for multi-threads or for non-uniform memory architectures. So if you're using more than a single socket, you actually want to have NUMA optimizations built in. Otherwise, your performance is going to degrade, even though you just added sockets, CPU sockets. And those are just not in place for these solutions. Single tier solution. So they
are not in place, meaning you have to do it either yourself or it's not possible at all.
It's not possible. You're just gonna degrade your performance if you use additional sockets.
Okay.
Right? Just because the implementations themselves are naive. Okay. Single tier solution means that your capacity is limited by the number of SCM devices and their capacity that you can plug into the system. Right? And SCM is not really cheap. And then the scope, the ambition is not really, it's not really compelling on that sense because they're not targeting to be enterprise grade storage. They're not going to implement all the features that enterprise grade storage has just because they have a local file system view of things, right? So there's a lot of difference in that sense, even though they do accelerate the I/O path. So that's true. The second type of solutions is basically handle the memory path, right? So I mentioned earlier, ext4 and XFS have a DACS flavor, right? It's not the same file system. You need to actually MKFS create the file system in a DACS flavor, and then doesn't support the exact same features as it traditionally does, but it does support you with direct access on the memory path or through NVML to the device itself, right? The advantage here is that it is a commercial solution. It's within Linux kernel and it's being distributed by several companies, just like any feature within Linux kernel. And but it does suffer from the same set of issues like PMFS and Nova. Again, it's not optimized. For NUMA in this case. It's a single tier solution. Again, you can't really extend the memory to traditional storage devices like we do. And again, it's a local file system scope. There's no high availability between nodes or single namespace or any of those types of things. Those have to be implemented within the application layer itself if you're doing that. And obviously, they only support one of the path. They don't support the duality of accessing SCM through either either mechanism. So Plexistor SDM in Contraire basically allows both of them. So you can access the same device, even the same data, not just the same device. You can have two processes, one of them using that data as an I/O path, and the other process using the exact same data, the exact same bytes in a memory path. And obviously, it's a commercial implementation. Otherwise, we won't be here. It does have many optimizations. Some of them I mentioned in the storage field day. I'm not going to go through that again. It supports multi-tiers, as I'll show in a couple of slides. And it's an enterprise-grade solution in terms of all the data services that are associated with that term. So here are the numbers that we promised for several times during that this talk. And again, the objective is basically to see how fast is this benchmark is only for the I/O path. Okay, it's built on the FIO benchmark. And what it basically focuses on is comparing ZFS, XFS, and our file system doing 100% random 4 kilobyte writes. Right? This is not the best case scenario. It's not the worst case scenario, just 4 kilobyte aligned
It's just
writes.
the usual ridiculous scenario.
This is the comparison to block. That's what you.
Right. So we tried, even though we can do byte level accesses as well, we aligned the benchmark to be 4 kilobyte aligned, so it's as fair as possible for block based solutions. But you can still see that in terms of throughput, when we're talking about 2 orders of magnitude improvement, in terms of latency, again, 2 orders of magnitude improvement in latency as well. Right, so even though they're using the exact same kernel version, they're using the exact same hardware, NVDIMM hardware and server, you get very different results. So I think the conclusion from this is that the software architecture and the software implementation of that architecture is everything in this new brave world of SCM. Another example that's not a synthetic benchmark. So in this case, this is Redis. Slides are slightly cut on the edges, but it's Redis, and we're comparing XFS, which is a lot faster than ZFS, so we kind of skipped ZFS in this case, and SDM underneath Redis. Okay, so most of these, another misconception, most of the middleware, like HDFS, like Redis, like Couchbase, like many others, they're not built, on top of thin air. They're basically built on top of a local file system. So that's why we use XFS and SDM as a comparison point underneath. And the integration with those middlewares is really easy. I mean, you just change the mount point. That's it. Okay. So when we ran Redis, what you see here is operations per second. We got 163,000 operations per second on average. The standard deviation in terms of percentages was very high. You see, it's very noisy, and you get these fluctuations in performance. So the performance itself is not really predictable. I mean, it could be a lot more than 163. It could be a lot less than 163 at any given moment, and you don't really know until you try, right? So you need to over-provision just to compensate on that. And then the latency. And this benchmark was optimized for throughput, not for latency, like many customers do, many Redis users do. But I don't know. So latency was 12.3, whatever that means, right? Millisecond. When we tested the same Redis scenario on the same server with SDM, you basically see that we have better throughput. So it's 73% higher in this scenario, and it's a lot more predictable. I mean, there is a variation in performance, obviously, but it's the standard deviation is 8 times lower than with XFS, right? So that's significant. And basically, that's a predictable quality of service that Sharon mentioned earlier, and also the latency itself is lower, 43% lower. Okay, so that tells you half of the story. As you see, half of the slide is still empty, right? So if you want to gain some insight into why is this happening? I mean, what do you need to improve to maybe even increase, that gap between the two solutions? You need some tools to go and analyze what's going on, have some visibility of what's going on in the infrastructure level, right? So today what you do is you use SAR, for example, which provides you with I don't expect you to see the numbers here, so I copied the main ones over here. It provides you with limited visibility. I mean, you don't really get to see, what system calls did Redis issue in that time, at a given time or on average. I mean, it's really complicated to get those numbers and what metadata operations did it use, and stuff like that. So, but what you can get is you can get some view on the CPU breakdown. So you can see it's like a third for user, a third for system, and a third for I/O weight, and then there's barely any idle CPU time on the machine, right? And that's a really common breakdown. What it hides is basically the fact that system performance is really poor. I mean, Redis is a user space middleware. The application is in user space as well. All it's basically leveraging, it's able to leverage is 30% of the CPU resources that the customer went and acquired. All the rest is being spent on storage. Well, storage and networking in this case, but mostly storage. Okay, so so in order to basically accommodate that, we've built very detailed monitoring tools into our software, into the SDM solution, and we have a graphical user interface that you can basically go and view, the entire history at any given point in time as well. And I don't expect you to see that as well. I mean, you've seen several graphs in your life, I assume, so it doesn't really matter, the exact representation of everything. But you can see over time, the exact CPU status, the memory status, and the network status, and obviously, get all the insights into the storage itself. Choose exactly which system calls you want to focus on, or aggregate it according to. See the metadata breakdown. Basically, have the entire visibility to what's going on at the storage level as well. And then if you look at the numbers, you can basically see that 35% of the CPU is actually dedicated to Redis. Then the system and the I/O wait time together, which is the bulk of the storage overhead, has been reduced to 25%. And 40% of the CPU basically is just idle. There's not enough pressure on this machine, on this benchmark, to basically leverage more than that. I mean, storage is idle. Networking is not idle, but has a lot of room. CPU has room, and basically what's missing is additional load that you can generate from the clients, or additional clients that will use the system. Okay, so it's a very healthy 40% buffer for additional load that you can use. So basically, if we added additional load, you would get higher performance in compared to XFS.
So the point of this is, with your software, you've got far more visibility into where you've got capacity to grow in performance.
Right. And also you can find out, inefficiencies in how applications use it. So it's very useful so I don't really expect, most of the users to open that. I think that, the entire point is being transparent, transparent infrastructure, but it is useful for application developers so they can understand what's going on, within their application. Okay, cost. So far we've been focused on storage class memory as if 100% of your storage is going to be built on top of storage class memory, or even a particular storage class memory type. So either NVDIMM or 3D Crosspoint or ReRAM or whatever, but one of them. And that's really expensive. I mean, if you look at all the different storage medias or memory medias that are here, you basically see that there is a very clear trade-off between performance and between price. I mean, that's probably not new to anyone. And SCM, again, not the SCM family, but the SCM tribe of families basically covers this gap here between DRAM and NAND flash. So there's no good reason to think that even as storage class memory gets adopted and gets lower prices along the next decade or so, that this phenomenon is going to go away. So maybe you'll see here another blob that's MRAM family and another blob here that's the ReRAM family and 3D XPoint in the middle. Maybe you'll see some different structure of different technologies that we don't know of yet or that I haven't mentioned. But in essence, you're still going to want to have something like hard drives or QLC or whatever type of flash that's really cheap for cold data. And you're going to want to have something that's DRAM speed and maybe something in the middle as well, right?
I mean, this was the same sort of argument that happened with flash originally. When flash was far too expensive, you then needed it's not a caching tier because it's a reverse caching tier. You had flash for fast and then hard drives for your capacity tier.
Right.
But as the price of SCM comes down, you're going to land up having the equivalent of all flash arrays today, all SCM arrays, when the price comes down. So how does... I suppose concern is that Plexistor's that part of your product where that part of your IP is for doing that is going to in a way become irrelevant because people are going to use SCM for everything when the price comes down, and maybe not have to use the slow flash as the caching tier, as the capacity tier. Sorry.
Yeah.
Luckily, they have a decade or so.
Yeah, so I actually think we have more than a decade. If you look at what's happening today, let's assume flash prices are cheap enough today, or stable enough today. You're not gonna. I mean, you will have all flash array solutions like Pure, for example, or Extreme IO. You're probably not going to use that for Dropbox for your files, user space files. Well, not user space, but user files. You're not going to use that for images. I mean, you're going to use S3 on the cloud or something like that as the basis for that storage. I mean, even if you look at Amazon, you still have two flavors of EBS. You have S3 and you have Glacier, so two types of cold storage as well. And obviously, you have the local SSD on the EC2 machine. I mean.
But the tiering component of your software isn't really the magic.
So it's part of the magic. I mean, you can use 100% SCM if you want as well. It's really up to the amount of money you're willing to invest in order to solve your pain point. I mean, that's entirely up to you. You have this single solution with SDM that you can change that ratio. I mean, if you open the UI, you see the exact penalty that you're paying for mixing those technologies. If you want, you can change that with time, add more memory, or add actually slower storage because you don't need that level of performance and you want a cheaper solution. Or you can even use 100% SCM. Again, it's very flexible and it's up to you. And SCM, again, it's not a single technology. Eventually, I guess you're going to have something like MRAM that's going to replace DRAM, and something like ReRAM that's going to replace NAND. But even if you look at NAND, again, you see different technologies that are tailored for different speeds and cost trade-offs.
So the caching tier is it's better to look at the caching tier for this example as more of a use case. As Alistair said, that's not necessarily the secret sauce. It's just it's another use case that you can use to more efficiently use your SCM memory.
I personally believe it's going to be, well, I'll put that slide right. I personally believe you need multiple tiers. You need auto tiering within those tiers. You don't want to manage that yourself through the application. I think it's going to be absolutely critical for wide adoption in the next decade. I think it's going to be very, very useful in decades to come after that as well. Not just the first decade, but a decade is a long time as well. So,
well, certainly it's time for you to build it It gives you enough time to build new features in.
Yeah.
Yeah. Okay.
So do you not see? Also, another one of the concerns is that obviously you've got a very clever Linux driver that you've built, which creates a file system view with byte addressable memory. Can somebody else not? Obviously, that's your IP, but can somebody not write an open source version of that? ZFS and XFS has its issues, but is that going to be extended because storage class memory is going to be something that Intel and everybody else is going to be seriously trying to punt out there, and that to be able to use that, you're going to need an efficient Linux driver.
Right. So we have a couple of years advantage. We have patents for that as well to protect us. Obviously, like any other software in the world, someone can, in hardware actually, someone with enough money can hire enough, many smart people and implement something similar. And I think that's good eventually, right? You want competition. We're not trying to be a monopoly in that sense. Although businesses like that, but
You might not be, but your investors would like it.
Yeah. Okay, but just another comment that the open source scope is typically a bit different. I mean, obviously that's an option. That's something that will happen. But a lot of the open source projects that you see are either very deep technology, single node technologies like a local file system, and then they don't really have the scope of enterprise storage with all the data and everything else, or a cluster view of things, or they're really higher level, Java implementations or things like that handle a cluster, but not necessarily in a very efficient way, and then they use underlying deeper technologies like the local file system on each one of the nodes. And so having the combination of something that's both cluster-wide smart and deep technology on each one of the nodes is something that's I'm not sure I know of any example today, but everything is a possibility right now.
Yeah, because I'm just trying to logically in my mind, and I'm not the super storage experts, because your product does a lot of different things in a clever way. Because something like Cassandra, for example, that is self-replicating. Initially, I was thinking, well, then I didn't get why the Plexistor software would be used for the replication part of the Plexistor software would be used for that because Cassandra is doing its own replication. But then if Plexistor is going to do that replication far more efficiently, and Cassandra is in a way going to see one local disk, which is actually which is therefore spread across a whole number of nodes, that could be a lot more efficient. So I think I get that. I get that part now that your software can provide that multi-host storage, but far faster than a native Cassandra on a local file system, for example.
Right.
Is that a correct understanding, or my?
Yeah. So actually, I have an example for Cassandra specifically. Obviously, not every middleware or application is going to use all the features.
Yeah.
But I think there's a lot of enough good things that you can actually sell for a subset of the features that we have and still benefit from that. But I'll show some example.
I would find it hard to buy the enterprise class label on any storage system that said applications have to be responsible for resiliency. Yeah,
you have that problem now, but the youngins, as you like to call them, are definitely moving towards that.
Yeah.
Yeah, and they're saying we don't need a storage system because my application provides the resiliency.
That there are those applications, but if you're going to say you're an enterprise class storage system, that implies very broad application support, not we run with these applications that do this, that relieve us of this generally accepted service that we have to provide.
But even there, for example, Cassandra is that layer. You may not have to write it into your application code. Your application code is going to store data in Cassandra, which is then going to be the distributed storage.
For the purposes of this conversation, Cassandra is an application.
Okay. Yeah.
Okay, so actually these are all good, very valid points, and I have an entire section on that in the next one. But in this section, I'm just focusing on the technology primer, so really basic features and
as a storage guy,
value.
I'm all for shifting my responsibilities to somebody else. It's like, sure, you can run SQL Server, just always running, always on, and then it's not my problem, and I'm good with that.
Okay.
Mark's an actual customer. He might have a different opinion.
So what I'm going to show now is several deployment options. Okay, so we talked about tiering, having multiple tiers, having different choices on each one of the tiers. That's basically the focus here. You see several other components that were mentioned along the way. I'm not going to talk about them too much now, like the graphical user interface we spoke about, the proactive optimization service that Sharon mentioned. We're going to leave that for a future discussion as well. We don't have enough time today. The bricks I'm going to cover later, and the cluster view as well. But what I want to focus here, which is the reason for this nice colors, is the hot tier, the warm tier, and the cold tier. Sorry, you don't have to have all three of them, right? You have to have a hot tier for persistent memory, but you don't have to have a warm tier, and you don't have to have a cold tier, and those are strictly optional. So, and I gave several examples within each tier. Those are different options that you can use. So for the hot tier, you can use the NVDIMN technology that Sharon mentioned earlier. You can use the P version that some vendors are building and are not yet available in the market today. You can use persistent memory, like 3D Crosspoint. You can use the brick, which we haven't explained what it is yet to a sufficient degree, but you can use that as well as remote memory. Or you can just use, if you don't really care about persistency that much, for example, if you're running on Amazon EC2 instance that can die anyway, because that's a contract, and maybe your application is fine with that, then you can use regular DRAM as well. You don't need anything more than that as the first tier of storage. For the warm tier, you can have obviously SATA SSDs, NVMe devices, LUNs from all flash arrays. You can use the shiny new NVM over Fabric appliances. All those are very valid technologies for the warm tier. And then for the cold tier, you probably want to use something that's a lot cheaper than that, something that's public or private cloud-based, some object storage, RESTful API like S3 and Swift, or NFS, or Ceph, or HDFS, or whatever other cheap and slow, relatively slow access media that you can get your hands on.
Are you saying there's no compatibility list at this point? It's any disk, any memory that's actually usable, anything?
So you're going to have very different performance on those levels.
But
right. So the most of the difference would rely on the health status of your and health monitoring of that device. Obviously, if you want to use something that no one tried before, then you could technically use it. You maybe not want to use it. So we do have a compatibility list that will probably grow with time. So you don't want to use just anything. I mean, even if you just use NVDIMN for this tier and nothing else, it's pretty complicated. You want to make sure you're using the right server with the right BIOS version and the right NVDIM. So if you go to HP, for example, and purchase that as a single box with everything in it, that's probably certified by HP, right? And you're good to go. But if you're buying some off-the-shelf server from from one vendor and then buying your NVDIMs from another vendor, assembling that without really understanding the technology, then you're going to bear that risk, obviously. And
so under the presumption that the hardware all functions well together,
right,
the Plexistor layer really doesn't care, it just uses it.
Right.
Wow, that's very cool.
And again, you can use the UI to basically debug your performance and understand if you chose the right amount and the right technology, and maybe try something else, until you're satisfied with that. And by the way, I borrowed the term Flexi-Plexi. It's not ours. I think it was the register that used that. So I'm going to reserve the trademark for them. Okay. Next feature, clones and snapshots. I mentioned earlier how persistent memory is a great fit for those for a very efficient implementation of those things. Like many other features, we needed to basically reinvent keep the functionality, but reinvent the implementation in order to fit the latency and the efficiency that's possible with this new technology of persistent memory. I'm just going to give some examples. Lightweight clones, like CP-reflink. That basically saves you the need to copy itself. So you can basically copy as many files as you want, regardless of their size, and pay nothing for it. So for application developers, if they want to have a application level checkpoint, for example, every minute or whatever, or many other use cases as well, if you want to have an image being used by several different applications, this is a really, really cool tool. It's been supported in kernel 4.5, that API, and I think there's a lot of, it's gonna have a lot of usage. I mean, we'll see, but that's my guess. Snapshots. So traditional, full volume snapshots for IT administrators, or specific per file or per directory snapshots for application administrators. I mean, this has been used in a long time, for a long time. We support those as well. We're talking about both read-only snapshots and read-write snapshots. I mean, that's, again, totally up to the user. And then the additional interesting feature of snapshots is the support for containers. So Sharon mentioned containers earlier as a great vehicle to have bare metal performance with kind of virtualization, ease of use at the same time. And there are a lot of storage vendors that talk about supporting containers and Docker or Kubernetes, and they have plugins for that. But that really is for the shared storage part of things, right? Not for the native storage on that local machine that's running the containers. And in our case, this is exactly where we focused on. So we're going to announce the support for containers in several weeks and show some results for that as well. But basically, you get all the benefits of the local storage, of the native, the external volume that people use in order to avoid the terrible performance that they get from overlay FS on top of ext4 or something like that on the local machine. And eventually the persistent storage, the shared storage that's available for everyone on as well, just collapse all three to a single SDM implementation, right? So there's no need to configure all three differently and use different solutions for all three. So that's something that's coming up. Stay tuned. Okay, after the long build-up for bricks, the hour and something long build-up, we're finally explaining what bricks are. So memory over fabric, or we call it as memory brick, actually is many different technologies. There are many different trade-offs within that technology. But let's talk about what are the usage patterns for that, right? So there are several different usages that have nothing to do with Plexistor that we can see. So that's the disaggregation of memory, of volatile memory or persistent memory in general. So that's the category. But in our specific case, we're talking about two main use cases. One is having a redundant copy of your data elsewhere, not on the same node that you're running your application. And what that means is basically high availability in the old sense, right? You have multiple copies, 2, 3, whatever number of copies, all available, all persistent, and you can recover from them on another application server. So that's the first use case. The second one is, as Sharon mentioned, is basically having your first persistent copy across the network, while the original copy that you're actually working with is on DRAM. So you don't need any persistent memory on the first machine, and you read and write to it and from it, but then you have another persistent copy on another machine. Okay, so those are two different use cases, kind of like the same software implementation for both of them, but the use cases are different. Any questions on those use cases before we go on to the technology itself? Okay. So what are the properties we're looking in for such an architecture, right? So we're obviously looking to maintain our very low latency that we're used to from the previous slides. We're looking to maintain the byte addressable access. Okay, we don't want to have some other solution over the traditional solution over the network that have to go through different software stacks or have the block granularity embedded within that. And kind of an obvious choice of implementation is we're going to build that on top of RDMA because that's what RDMA does. Maybe not in a persistent manner, but that's what the technology was built for. So before I go on to different types of devices, just to see one example. So this is a demo. Well, actually, this is a screenshot from a demo we built with Mellanox. And what you see on the left-hand side, you see a single node, the latency of a single node, right? The application server, just like we spoke in the previous slides. You see the latency here is 3 microseconds. The reason it's 3 microseconds is because it's running 1.6 million operations per second. Okay, it's not the maximal that it can do more than that, but just the 100 gig interface in between the machines can't really carry a lot more than that. And even if it can carry 25% more than that, the latency is going to go up. So we kind of chose near 1.5 million ops per second, thinking that's going to be good enough for most applications in the world anyway. And then you see here the latency for this exact same benchmark, just in a brick configuration, where you actually have a persistent copy on this node, and then another fully synchronous copy on that node as well, right, on the brick node.
That's only over 100 gig Ethernet.
No, so it's available on any RDMA supporting technology. These numbers are from 100 gig.
10 gig Ethernet, it might not be 5 microseconds, it might be 8.
So first of all, it's not going to be 1.6 million, right? Let's start with that.
Yes!
Yeah.
And then it's not going to be that latency as well.
Okay, but what is the figure just between the application server
It's
and the PM?
5.4 microseconds.
100 gigabit.
On the line.
100 gigabit. Right? So we've measured with other RDMA technologies as well, with other speeds as well. This was done with Mellanox, and they have their 100 gig NICs, so and switches. So these are the numbers that we present.
Gee, I wonder why Mellanox.
Okay, so what are the brick types that we envision? Okay. So first of all, it's many brick types. It's not going to be one brick to rule them all. You can have volatile memory bricks. You can have persistent memory bricks. You can have different implementation, different SCM technologies going into those bricks as well. Some of them placed on an NVDIMM form factor. Some of them placed on a PCIe form factor. Then, perhaps more importantly, you're going to have hybrid bricks, right? Maybe you don't need to access all the data all the time as a mapped technology. Maybe files that are closed, for example, or maybe just data that is warm and not hot. Maybe you can place that on a cheaper device, right? So we also built into the protocol the notion of different tiers within the brick itself, and the initiator provides the hints for those tiering, right? So you can basically use persistent memory and SSDs, and the initiator will say, I don't really need that data, that chunk of data anymore. You can basically tear it down. Obviously, if it doesn't support tiering, it will just ignore the hint, and that's it.
That's all within your software, always done.
Yeah. And then you can envision a scale-out brick architecture as well. For example, have a brick on every rack, and have some coordinator between them to load balance that will either prefer locality or load balance if one of them is becoming full to other, or becoming too busy to other nodes. And that's why we basically said, you have your traditional RDMA, you have some enhancements to the RDMA, mainly around persistency, making sure that the data you wrote is now persistent, and that's being proposed by SNIA, by Microsoft, by several other partners as well. That has already been addressed. Well, being addressed, more accurate. And then the out-of-band control is basically to provide the tiering, to provide the scale-out. It's a very simple API. We've already shared that with several partners that will hopefully build their own bricks flavors.
So when you say build their own brick flavors, this is the hardware supplier onto which the Plexistor software is installed as a layer?
That remains to be seen. Either they'll build their own software.
Whether it happens before.
I mean, the protocol itself is open, so everyone, and the Linux implementation for the library on the application server side is open as well. So everyone can basically use the same API, and everyone is invited to build their own bricks as well, right? It does. We obviously have our own brick implementation for R&D purposes, at least, right? For demo purposes.
Do you need software on the brick as well, or just on the application server?
You don't need to. You don't need that. I mean, you can use it there. It provides some benefits, but you can build your own. Okay, clustering. So clustering is a very, very wide topic. I'm not going to talk about it too much, mainly because the current implementation that's available for download doesn't provide that feature yet. So there are different levels of implementing clusters, right? The first one is basically just viewing in the UI, just in a single pane of glass, viewing all the different nodes on a single UI. That's the easiest. That's supported already in the GUI today. Another one we already mentioned is high availability, managing where you have secondary and tertiary copies of your data within the cluster. And then the hardest one to implement is basically the single namespace feature. And that means being able to access any file from any node, regardless who created that and where it actually resides at the moment. Now, our architecture is very, very, very different than distributed or clustered file systems that you're probably familiar with. And the main reason for that is that it's all focused on latency, which is typically not the best property for existing clustered file systems. I mean, they're very good at having cheap and deep storage, maybe throughput-oriented storage as well, but basically not small accesses or anything that's good on latency for any of the scenarios. So again, we maintain the single software layer for the speculated path, right? We speculate that the data is going to be local to the machine. If that's the case, and that's what we strive for, so that will be the case in most of the cases, latency is going to be exactly like it was before, right? Having a cluster and a single namespace is not going to degrade your performance unless you actually share data across different nodes. So for that particular byte range of that particular file, you're going to have lower performance, obviously, right? But for the rest of the data, which is the majority of the data, usually they tend to have a single user, or at least a single updater for that piece of data. And that's going to have the exact same latency that it has today. I kind of mentioned that before, right? We strive for data and metadata locality. So we're not going to uniformly spread the data and the metadata across the cluster. We're not trying to get the last gigabyte of data available from a node across the fabric. That's not the design point. The design point is latency. So yes, it's going to be a bit less efficient in terms of capacity usage, but you're going to have the latency that we guarantee for that. Yeah, and the last point is actually a philosophical dilemma. I mean, you can do two types of scheduling. Hopefully, the scheduler on top of us, being Docker, for example, or whatever, or OpenStack, or just the user himself, is going to schedule the compute to the right data node. Well, not data node, but to the right node that has the data with it, carries that data. That may be impossible in some cases because your data resides on multiple nodes and you just have to pick one. Today, most of them are agnostic to that, so they just randomly pick one according to where they think there are enough, CPU resources, etc. Everything is fine. If the scheduler on top of us doesn't do that, we'll basically do that instead. We monitor the usage of data, and we change ownership of the data and the metadata according to the usage pattern. Right? So it might be slower at first if you schedule on the wrong node, but eventually we'll move all the data and all the associated metadata if there is no competition, obviously, for that particular piece of data. We'll move it to the right node. Right? So all that is built to maintain latency goals. So to conclude this section, actually we have another section on big data, which I promised earlier. So to conclude this section, we're going to run multiple applications, existing applications, new applications, existing programming model, new programming model, whatever. They can use it as storage, they can use it as memory. We're going to do everything behind the scenes, behind the local file system API, trivial API, to make sure that they can use multiple tiers, they can have all the features, and they can have the latency goals that they want without having to change the application itself. Right? So basically reinventing the entire software infrastructure, but maintaining the application as is.
Interesting you don't ever mention it as a virtualization layer, which everybody else does. They always...
We don't have a virtualization layer. Layers add latency. We have everything embedded within a single layer.
I think, that's deliberately worded, because in a way you are virtualizing disk, flash, and DRAM.
Yeah.
So it's a deliberate choosing.
I'm kidding. Okay, so there's a free SDM download. It doesn't include all the features, but it includes most of them, or some of them at least. That's available online. And we're coming up with a new version in 2 weeks. That includes additional features as well. And then we have a blog, which people interested in that level of the technology, not just to use it, are welcome to follow as well.